Thanks everyone for coming. It's really good to see everybody here. Good to be back in person and looking forward to the summer to, spend more time with everyone and take part in these CEMDI seminars. Today, I am talking to you about bias in diffraction data analysis. Maybe diffraction data analysis is probably familiar to some of you, and trying to see where the limitations are and where the room for growth is. So this isn't going to be a lot of solutions. It's more of the purpose of this seminar is to open people up to discussions and further development in the future to hear more about what problems you might be facing in this realm and what we can do to solve them. Bias in computer vision and artificial intelligence has been in the news recently, mainly due to the use of facial recognition technology. And this is where from an image or a photograph of someone, it's processed by a computer, and then it's compared with a database of photographs of other people, and then trying to match the person with the right person in the database to make their identity. And this is useful for law enforcement. This is useful for people, also for immigration and other sorts of markets. And it's big money. I mean, this is going to continue to grow. And by 2030, it's expected to reach over $22 billion value. So the issue with this is that there's a clear bias in the algorithms and in their ability to identify people correctly. And a bunch of different algorithms were compared in a study in 2018. And what it found is that there's a systematic bias to identifying lighter skinned males as opposed to darker skinned females. So this is troubling because especially if you're in law enforcement, you don't want to get the wrong person. You can ruin someone's identity. You can ruin someone's life basically by falsely accusing them of crimes and such things. And so since 2018, a big push has been made in the community to try and improve this. And they have made improvements, but this is still an ongoing problem in this sort of image recognition field. Now, my dream is something similar, where instead of identifying people by their faces, I want to identify materials by their diffraction patterns or by images of the material as well. But I'm not going to talk about real image recognition in this talk. I'll be focusing on just diffraction data analysis. And so the concept is the same. I take a diffraction pattern, whatever it is, and I compare it with the database, and then I try and find the match to identify the material and the structure, the microstructure, identify all things about that material to the best of its ability. And so this talk, instead of skin tone and sex, I'll be talking about when does this work in terms of purity and crystallinity. So in the left side, this would be an amorphous, and you can have very pure amorphous materials. And as you increase the long range order in the material, you become a perfect single crystal, and everybody's idea, real physicist's idea of a crystal, I guess. And then, but you can have mixtures, varying degrees of long range order and varying degrees of purity, mixtures of phases, phase segregations, and all sorts of defects and other interesting aspects of the microstructure. And those I just kind of lump down here. I don't want to be too microscopic and split up purity, but we're just going to be talking about when could we do this in the mapping of purity versus crystallinity of a material. I want to first introduce why I'm interested in this. Like, for me personally, I'm very interested in studying metastable polymorphs of materials, because by controlling and changing the microstructure and the structure of material can influence its properties. I mean, this is something that everyone might be aware of, but I just put two textbook examples up here. This is carbon in both cases, obviously, This is amorphous carbon black, and it's a conductor. It's very ductile. It has also, you use it in tires and things like that. And this is diamond, so it's hard. It's an insulator. Has a band gap, and so these are very different forms, and it's just carbon. And one thing I want to point out here is that these are actually both metastable phases of carbon. So metastability doesn't mean instability. We still have diamonds all over the place. We still have carbon black. The stable form of carbon is graphite at room temperature and pressure. So studying these sort of different polymorphs of material is interesting in order to be able to control its structure and bring out new properties. And it doesn't mean that it's going to disintegrate as soon as you synthesize it. In the sort of computational material science world, people have done a lot of work in order to be able to try and predict these polymorphs of materials. And here is a really nice paper by some of the people involved in the materials project, which are really spearheading this effort. In the red crosses, these on the y-axis, you have the energy above the ground state. So it might be stable, but it's not in its ground state. So if it's purely in a metastable state is basically defined by all of these configurations that aren't in the real ground state structure. Versus for a few different materials. So we have zinc oxide here, iron oxide, titanium dioxide, vanadate, and molybdenum oxide. And you can see the theoretically predicted polymorphs versus the observed polymorphs. And you can see that there's a whole lot more theoretically predicted polymorphs. So the question is, are we that bad at synthesizing things? Are we, you would think with hundreds of years of modern scientific method and chemistry and development of physics and measurement techniques and characterization, like why don't we see this polymorph here, even though we see rock salt, which has a much higher energy above the ground state. So what is really the limiting factor for deciding whether or not we see a polymorph theoretically, experimentally compared to its calculated energy? And the answer is that you have to, beyond just the thermodynamics, you also have to consider the kinetics of how these polymorphs, or how the material crystallizes and evolves through a solid state or phase transition. And so these authors made the important distinction that in order for a metastable polymorph to be observable, it has to eventually have an energy which is favorable at some point compared to the ground state. So we have here the energy of a crystal for metastable phase M versus stable phase S as a function of crystallite size, right? So we start our experiment by crystallizing this stable phase S, and we go out of a supersaturated solution. And at small crystal sizes, due to maybe the surface energy contribution, the metastable phase actually is favored. And so you grow first a metastable crystal, and then eventually this will become, there'll be an increasing driving force. So in other words, there'll be a favorable transition onto the stable phase S. And when this driving force gets large enough, you'll start to nucleate the more stable phase, and then this will be swallowed up from the metastable phase, and eventually you'll grow the stable phase. So if you look at the end and at the beginning, you might say, well, I don't see this metastable phase because you have to be able to follow these sort of kinetics. And to be able to answer this question of which metastable polymorphs are really observable out there, we have to get better at being able to follow these phase transformations and phase transformation kinetics. So that's pretty much why I'm interested in using the dynamic transmission electron microscope to be able to study these sorts of transformations. And it's a very unique electron microscope where you're able to take nanosecond and nanometer time resolution images of these irreversible processes, like such a crystallization or phase transformation event. And so how a sort of an experiment will work, we trigger the transformation, and this can be by an excitation laser pulse. And then synchronously, we generate nanosecond electron bunches via UV laser, which you can actually have arrive in a train. And then, we time up the arrival of this train of electron bunches with the excitation of the sample in order to capture a series of snapshot images of this sort of a phase transformation. And so what I'm showing here is actually the crystallization of a germanium alloy, germanium tellurium antimony. So it's a GST, which is what's it called, phase transition alloy? No. But anyways, it's a germanium alloy, and you're seeing it going from an amorphous into the crystalline phase based on the laser radiation. And this is material which is actually in DVDs and CD-ROMs. And this is how you write bits onto DVDs and CD-ROMs. So the 0 would be the amorphous region, and then you shine a laser on it, and then you're able to get it to transform into a crystalline region. And then those two have different reflectivities, so you're able to write a 1 and a 0 based on the reflectivity. The thing is that this is a rather chaotic process. You can see by just changing the laser energy by a little bit, you get very different microstructures of these materials. It goes from a single nucleation point into multiple nucleation points. And they grow in together and have different ending defects and ending microstructures in the end. And so this has been used by the group in Lawrence Livermore, so the people who developed the DTEM, as a proof of principle experiment to show we can actually capture these sort of chaotic, irreversible phase transformations. Similarly, you can do time-resolved electron diffraction in this experiment, in this microscope. So this is showing the transformation from an alpha to beta nanocrystalline titanium, and just seeing that you can capture also the diffraction pattern as well as the image in the microscope. But this poses a problem because the characteristics of the material and the microstructure that you're going to be analyzing at each time point, it doesn't have very long range order. It's rather transient and in a non-equilibrium state, so you can't apply your traditional expectation of what the structure of the material might be. It's inhomogeneous across the probe region, perhaps. I mean, you can already see here, if we have if we're probing the diffraction pattern from an entire region here, you're getting a mixture of both amorphous and crystalline contributions, and it's different kind of every shot. So this poses a challenge to the analysis of this diffraction data. And so in my group, kind of how I fit into the CEMDI umbrella, or how I see myself working into CEMDI a little bit, is that we are developing the experimental techniques in order to go from the real experiment in the microscope, collecting the data, but then also the analysis techniques in order to be able to perhaps plot the phase fraction as a function of time. But this needs complement complementary understanding from, sort of a heat flow models of what sort of heat gradients we're producing in the material due to the laser irradiation, plus some sort of kinetic model of expectations of these sort of energy diagrams for the different phases as a function of temperature, in order to have a real theoretical understanding of these curves that we're producing, and then feeding back into refining the experiments from the theory, and refining the questions that we can answer with this tool, with this instrument that we have. So that's sort of how that's why I'm interested in the computational material science going on here at INRS as well. So let's go back. So that's why I'm interested in this and why it's an important question for me. Let's go back to the sort of topic of this seminar, which is to discuss what is really the problem with this diffraction analysis. I mean, it's pretty textbook, where you have a beam of irradiation, you put a crystal in front, you measure Bragg spots, and then a computer gives you the structure. What can go wrong here? So I wanted to start first by asking, who's ever done like a single crystal diffraction experiment, X-ray or neutron or anything? Okay, so we have some experience in the room, very good. For those who aren't familiar, normally how this goes is you have a sizable single crystal. I mean, you can see it, and you put it on a goniometer, and you can rotate this in all three directions in space, and you have a source and a detector over here, and you measure the Bragg reflections throughout all of the different orientations of this material, or this crystal. So whenever you rotate the crystal, you change which Bragg reflections that you obtain. And when you have a full 3D map of the intensities in reciprocal space, you can use phase retrieval structure solution in order to retrieve the electron density map. And then you try and fit that electron density map with an atomic model. So going just from here to here, I mean, this is probably the hardest step, is being able to really extract the phases. And this has been the push of, crystallography for the past 100 years, is developing methods in order to reliably extract the phases and to be able to solve for the electron density map. So just to kind of fill up our table a little bit, when does this work? This works when you have a big crystal, you don't have too many atoms in the unit cell, they have nice long range order and nice Bragg peaks. So single crystal, yes, we can do that. We can identify the material with when we have a nice single crystal. But what about powder diffraction? Who's ever done powder diffraction? All right, good. That's where I did my PhD in, is in powder diffraction. And so in powder diffraction, you have what's called Rietveld analysis. And instead of measuring Bragg spots, you get these rings due to having a powder of material in the beam in all possible orientations. And so you have these Bragg peaks that you're able to measure in the powder diffraction pattern. And just by being able to fit this, you can identify which peaks you have, and then you compare that with a database of other materials. And you can see, based on some basic chemical information, what sort of phases might be possible to exist in your powder diffraction pattern. So, so going back, that means that we can do this. The issue with this is that when you have too many phases mixed in, so if you have more than one or two, it becomes challenging because you have a lot of peak overlap. And also when the symmetry and the unit cell becomes large, or when the symmetry becomes low, then you get a lot of overlap, and this becomes a more ambiguous process. But we'll still say, okay, pure polycrystalline material, we can do that. Amorphous materials. How do you identify the structure of an amorphous material? Anybody done pair distribution function analysis? No. Okay. Okay. A few. So we're dwindling down our good. It's good though, having people from different viewpoints. So in pair distribution function analysis, you have a problem where you don't have well-defined peaks in the diffraction pattern. It's just a nice, from an amorphous material, what you get is a very smooth, broad, continuous signal, basically. But you can still treat this signal with some mathematics and take the Fourier transform, and you're left with the pair distribution function. This is just the conjugate of the measured intensity. And so then each peak in the pair distribution function, you can use that in order to measure. This is actually your sort of bond lengths within. And so then you can get local structural information. So this is useful. So you can characterize the local structure of amorphous materials. But this becomes a problem again when you have mixtures. So basically, to answer when does this work, this question that I posed and sort of the topic of this talk, it works whenever you have a really pure structure and you can span the crystallinity. And this has been, the development over the past 10 or 15 years. But it starts to break down anytime that you actually have a composite of mixtures of materials, polymorphic or complex microstructure, where you have also lots of defects and mixtures of all of these things. Now I wanted to show what does the diffraction pattern from multiple crystals kind of look like, to argue that it's not a problem of the data. My argument is that it's a problem of the analysis that we currently have on hand in order to be able to expand the applicability of structure determination. So you can see the circles here are the predicted spots from one single crystal, but you can see that there's a bunch of other Bragg spots in this diffraction pattern, but they're not overlapping, which means that the information is still reliable in those pixels. And so what we need now are algorithms that can identify what are the other crystals, what orientations and what other polymorphs do these Bragg spots correspond to. And I will be talking to you, kind of showing you some examples of this state of the art based on some work that I did doing serial crystallography while in the group of Henry Chapman in Hamburg, Germany. And serial crystallography is where you kind of use a small, tightly focused beam, could be electrons, could be X-rays. So your probe beam is small, and then you translate your sample in front of this small beam, and you rapidly collect diffraction patterns from, reading out your detector sort of as fast as you possibly can. Here's a setup for an experiment I did at Petra 3, which is a synchrotron in Germany. And we had a powder of terbium bipyridine nitrate. We sandwiched it between two pieces of Kapton tape, and then we just ran the tape, just like a cassette drive, basically, and rapidly took diffraction patterns of whatever was in the beam at that time. So here's a movie of the data stream coming in. You can kind of already see sort of the heterogeneity that you get when you get these sorts of measurements. You see images or diffraction patterns with well-defined small Bragg spots, but then every once in a while you start to see these lots of diffuse intensity, really interesting streaks. There's more symmetry there. There's more information there. Let me play it one more time, just because that was a little fast. But it's like a water hose of information flooding in. And how do you parse through this? And how do you identify and actually make use of all of this is sort of what I'll be talking about next. This isn't the only way to do serial crystallography. I was also involved in doing it at X-ray free electron lasers. And there you have the issue where you destroy the sample due to the high intensity of the X-ray beam. And so we, instead of translating on a Kapton tape, what we did was we streamed the sample in a microjet. And we just streamed by crystals in a microjet and collected diffraction patterns on a series of detectors. But you can also do this at in an electron microscope. So this is the work of Stefan Schmitz well, he's Dutch, but this was done in Denmark when he was working in Denmark. And here you can do a serial crystallography experiment where you have your particles distributed on a grid or a microstructure, maybe a thin film or something like that. And you sort of take low resolution images first, and then you start to identify regions of interest in these low resolution images. And you go back and you focus your beam and you zoom in on a given crystal, and then position your beam there with the deflectors and collect a series of diffraction patterns from different crystals. And this is important. This could be interesting for samples which have more of a beam sensitivity or a dose limit of what they can really tolerate in electron microscopy. So the computational challenge is that you have megapixel detectors. You're talking about 10 to 100 hertz repetition rate, which translates into gigabytes per second and terabytes per hour. So how are you able to do this automation? You can't flip through these images and cherry pick and put this together. What we really need is a more automated approach to doing this. And so the steps involved are spot finding, indexing, which is determining the orientation of the crystallite, merging it into reciprocal space or integrated intensity, and then solving the structure. And we'll go through sort of what works in each of these data analysis steps and what needs work in these data analysis steps. So, oh, you can't see that at all. I apologize. Spot finding is pretty much what it is. You take an image and then you try and use an algorithm in order to be able to determine are there any diffraction spots in this image? If you're looking for them, then you want that. If you're not looking for them, then you don't want that, obviously. So that's the first level of parsing this this data set. And the way that this works is you can't just simply threshold, because you actually have a lot of variation in the background. And so what most people do is sort of a windowed filter, where you look at say a 10 by 10 window of pixels, and you go through the entire image, and you look and see if you have any outliers from the median value or the background value. And you define that as a potential pixel or set of pixels that has a spot. And this works well when your spots are small and sharp, but it doesn't work well when you have more diffuse spots. And here, these are spots that are coming from a sample of PCMO that I collected at LCLS. And these are obviously extending more than just a few pixels. So your window has to be larger to be able to properly accommodate for these. But then you begin to get into a very philosophical question of what is a spot actually? You know, is this one, or is this three, or is this, you know, and how do you identify what is the useful information in this spot? So this kind of diffuseness and spreading is actually caused by faulting and strain in this material. And we would like to also have access to that information. Being able to understand the degree of faulting also is important for characterizing the properties of of material. So what needs to be worked on in this is to really be able to properly identify and handle more of these diffuse spots and be able to classify and be able to extract more information from them. So to fill in our table, moving on to indexing. So indexing is really determining the orientation. As I said before, as you change the orientation of the crystal and the beam, you're going to get different Bragg spots that you observe. And you can use which ones that you see to go back and determine what was the orientation of the crystal in the first place. And most indexing algorithms actually are based on a Fourier transform approach. So this works where this is a nice single crystal diffraction pattern. Lots of spots going to high resolution, well defined. And if you just take the dot product of each spot with this vector along here and histogram it, you're going to get a sort of you get a distribution like this. And if you take the Fourier transform of that, then what you have are regular peaks. And you can see that this regularity allows you to back out the unit cell constants. And so then you can identify the orientation of which planes these peaks correspond to based on this Fourier transform analysis. The problem is, if you have a different vector along a different direction, then you don't get a very nice histogram with regular peaks. And when you take the Fourier transform, it looks like noise. And so this way you can also identify what are teach a computer how to identify what are our eyes can obviously see this pattern very easily, that this is a rotated sort of square pattern, but a computer, this is how you can classify that this is the one primary axis and this is another primary axis, because you get nice peaks in the Fourier transform along those directions. But when you have multiple crystals in the diffraction pattern, it again looks like noise when you take this Fourier transform, because you don't have as much correlation. You have too many competing orientations to allow you to use this Fourier transform algorithm. And so I worked with some colleagues at the Danish Technical University, Søren Schmidt, namely, to develop a new algorithm in order to solve this problem and to be able to index these multiple crystal diffraction patterns. And so again, here is our problem. We have our detector, and we can define a vector for this observation. We'll label it a G. And then what we want to find out is which HKL corresponds to that observed vector. Or in other words, what rotation do we have to do in order to bring the proper HKL onto the observed G vector? And just to dive into this a little bit, because that's sort of the point of these CEMDI seminars, is to give a little bit deeper understanding of how these algorithms and computational aspects work. It is based on an approach, it's called in Rodriguez space. So you could decompose all of the possible, so given an observed vector, a G vector, and you want to see what are all of the possible rotations that you can do in order to bring this HKL vector onto that G vector, you can map that out into Rodriguez space. And so this can be decomposed in Rodriguez space into two sort of primary vectors. One is where you have a rotation, which is the smallest angular rotation necessary to go from this HKL and map it on to the observed G vector, and that, like, we call it R1. So this angle that you have to rotate can define this axis of rotation, and then you have the minimum angle necessary, and then you also correspondingly have the maximum angle necessary. And this is about the vector, which is actually directly in between the G and H vector. So whenever you have two vectors on a unit sphere, the smallest angular rotation to bring one on to the next is the normal to the plane defined by those two vectors, and the longest is about a vector that is in the plane defined by G and H. Does that make sense? Sorry, I just sort of making sure I haven't lost you completely. So then you can, all other possible ways of bringing these of mapping the HKL onto the G vector can be represented by a linear combination of these two transformations. And in Rodriguez space, a given orientation operation corresponds to a point. So it's defined as a vector. So it's just a way of thinking about orientation transformations in a three-dimensional space. That's what Rodriguez space is. And so what we have from our definition of these two sort of orientation transformations, mappings, is a line in Rodriguez space that we can define. So given an HKL and an observed vector on our detector, we come up with a line in Rodriguez space. And then that means for every observed spot and every HKL, we get another line. And so what the algorithm then does is it goes through Rodriguez space and tries to find intersections of these lines. And so these are likely places where you have those spots corresponding to crystals of the orientation defined by the transformation where all of those lines in Rodriguez space cross. Okay, that's the picture view. I didn't want to dive into the math, but that's the picture view of what the algorithm is doing. Let's see how it performs. So here, this is an overlap diffraction pattern of 10 crystals of simulated. This isn't real data. This is a simulated diffraction pattern. Random orientations of this zeolite. And we can see that down here we have the correctly indexed crystals per image versus the simulated crystals per image. So we're able to, when we have, all right, let me back up a second here. In order to produce this graph, I ran many sorts of these simulations. So I created a large data set of different simulated diffraction patterns. And then I fed all of those into the algorithm, and I knew the orientations of the crystals ahead of time. So then I could compare what the algorithm produced versus what I knew the answer to be. And so you can see in the blue, the number of correctly indexed crystals as a function of crystals per image. So, and there's also how many correct versus the found numbers of crystals. So in other words, it can still find extra, but then if you have, say, 10 crystals contributing to that diffraction pattern, the algorithm might find 15. And so then how many extra patterns, how many extra crystals is it finding? So that's the other metric that I have over here. So what we can say is that for some crystal classes, it works quite well when the crystal symmetry is high. It works quite well. We're able to index even up to, say, pretty close to 50 to pretty good accuracy. And this degrades whenever the crystal symmetry decreases. So when we have lower symmetry, this algorithm doesn't work as well. And then maybe you say, well, your cutoff is more like 15 to some reasonable accuracy. So this still needs some work in order to, that's just one approach, and it works for pure mixtures of polycrystalline materials, but it doesn't work well when you also have polymorphic, so multiple sorts of different crystal classes all mixed together. Now, again, now we move on to merging. Once we index, you know what that HKL is, so then you can populate your three-dimensional reciprocal space. So you can add up all of those integrated intensities. And I just like looking at these patterns, to be honest. That's why I put this slide up here, because it looks like a Persian rug or something like that. It has very striking symmetry, and you put a little color to it, and it just, you can tell, this is how, you know, you can tell that there's information in these diffraction patterns. I mean, it's, you can get, and so what we have here is the HK0 plane, so kind of the zero, cutting through the zero plane of reciprocal space for lysozyme. And here, this is the terbium bipinitrate that we talked about in the beginning, merged up after doing the sort of integration and merging. But you can go further, because you're throwing away a lot of information just by looking at the Bragg intensities. So you also have information around each reciprocal space point, which is this diffuse intensity. And even still, you have information which you can't quite tell in a given diffraction pattern. So this is a single diffraction pattern from, this is photosystem 1. This is another membrane protein. And so are these spots? I mean, this is, again, this diffuse intensity. But if you use the information about the orientation from the Bragg spots that you do have, and then you take these full detector images and you merge them into 3 dimensions, you can see that you have more structure and more information about the structure of material extending up to a much higher resolution in reciprocal space. So this is the sort of state of the art, we're just starting to get these big data sets of diffuse intensity. And so then being able to interpret this information of what is this telling us? And in this case, they were able to use this in order to extend the structure, the refined structure of photosystem 1. But like I said, there's many different things that contribute to the diffuse intensity that you see. And so there's still a lot of room to work in order to be able to analyze this diffuse scattering intensity in reciprocal space. And what I would like to do is then sort of do crystal classification, just basically looking at this diffuse intensity around a Bragg spot. So moving right along, the last step is trying to solve the structure. And there's, like I said, this is the phase problem. This is the classical problem that is presented in every crystallography class. How do you go from, when you even have the integrated intensities, how are you able to get the actual structure out of it? The Persian rug looks nice, but this is really the information which is more relevant to what we need to know. And so one way to do that is molecular replacement. And I wanted to mention this because bias is a main problem with this phasing approach. And the idea of molecular replacement is that you use a structure which is similar, which is already solved, and you sort of use the phases from that structure, you know, as a starting point, and then refine the electron density that you recover based on this model, this initial model for the phases. And this works when you don't have a lot of extra information that you have to obtain. So this is another membrane protein. This is cathepsin B. And what they were able to find is this extra wire mesh. So they had the information about the rest of the body of this protein, of this solid region, and they were able to use the phases and then use molecular replacement and also obtain, when you did that, you found that there was extra electron density kind of hanging out around it, and they were able to actually fit the atomic model to it to show that it's actually you know, useful information. But the problem with this approach is the bias, the inherent bias you're highly biased by your starting assumption in the initial structure. In inorganic materials, the sort of approach generally is to use direct methods. And this has its own limitations. And this doesn't have any inherent assumptions in the phases. So you can solve structures a priori in this method. But it requires high resolution data to be able to use this. And this is because what you're looking at is sort of rule of thumb relationships between pairs of reflections in reciprocal space and the structure factors. So what I showed here is just one of these rule of thumbs, and then there's like a whole bunch of different comparisons that you can do to try and have likely values for the phase solve the phase. But given, if you have structure factors for a given HKL and 2 times, so in other words, if I have the 100 and the 200 structure factors, and they're both large, then most likely the phase for the 200 reflection is 0. And this argument comes from trying to look in real space and saying that if you have a strong, this would actually be, if you have a strong reflection, for this would be the diagonal, so this would be the 110 actually. So if you have a strong reflection, then you're going to have a lot of electron density at the nodes in the 110 reflection. And then if you look at the 220, it's unlikely to have this sort of phase mismatch. So this would be the case where the phase is non-zero, because you can see that you don't have the high electron density going through the center of your unit cell. And it's more likely that if both structure factor from 220 and 110 are big, that you have these overlapping of electron density. And that's sort of the essence of direct methods, is using these reasonings to develop a library of arguments to limit down the possibilities of the phases. But again, this has a problem of obtaining high resolution data. But I used this on the data set that I showed you, and I had to index all the way up to 288,000 crystals. And that came from actually 187,000 images in order to be able to get the resolution to the extent and the signal to noise ratio to the level to be able to solve this structure. And so is it really necessary to go to that level? Necessarily, only if you want to. That's limited by the sort of the structure determination algorithm that you use at the end. But there is still a lot of reliable information at lower resolution that was sort of unattainable. And this is the structure that we found. This is the structure of terbium bipinitrate, and it's actually compared with another single crystal method to show that it overlaps well. So it's correct, but to collect this much data, it took, hours of measurement time. So we still need to improve the structure solution, decrease the bias, and improve the methods in order to solve the structure of materials, to expand the applicability to more microstructures and more types of data. So if you look at when these sort of data analysis steps, what they work for, they all work for single crystals. And this is the punchline, right? And this is what I've been saying. What needs work is all of the data analysis in order to be able to really interpret and study more complex polymorphic and polycrystalline microstructures. So this is really, I see the future of diffraction data analysis and the necessary computational hurdles that have to be overcome in order to realize it. And this is summarized sort of in this slide. And also pointing out that we have diffraction data analysis is creating immense amounts of large volumes of data. And so doing this automatically and doing this sort of guided by computers as opposed to these rules of thumb is really necessary moving forward in the future. And I kind of wanted to close with to start a discussion. I talked about bias in diffraction analysis, and I know that there's bias and limitations in almost any sort of analysis. And so just to sort of spur perhaps some discussion, I wanted you to kind of take away reflecting on what are the fundamental limitations in bias in the analysis and that you deal with in your work as well. And I'd like to thank you very much for coming. Thank you.
For a wonderful talk. Questions?
Another question. So in one of your first slides, you showed metastable states for different chemical compounds. So this is obviously the result of calculations. And
Yeah.
There were only few observed states.
Yeah.
So it's very surprising that there are so few states really observed.
Yeah.
So I was wondering, the calculations, can that tell us anything about how to synthesize those metastable states?
Oh, yeah. Well, so the question is, how can calculations give us more insight into actual synthesis? And, you know, you have to consider beyond just sort of a frozen structural information. You have to consider the other contributions to the free energy of the material to be able to begin to simulate the actual kinetics of the transformation. And so, yeah, I'm just starting to learn more and dive into this. I would say I can't say exactly what the solution is, but understanding more about the exactly what is the free energy throughout the phase transformation, to understand which phase has a lower Gibbs free energy at given moments during the transformation, gives us more insight into which ones will really be observable. Because maybe the ground state has a lower energy, but you'll never see it because you never cross, it never actually, the total free energy is never actually lower than other phases, basically. But it's, yeah, it's interesting.
Yeah, I have a question about the identification of phases when you try to look for needle in the haystack. I presume one of the issues would be hoping that in a large batch of a crystal or a mixed phase system, you're occasionally going to have these rare metastable phases that for whatever reason may exist. So when you look for your diffraction pattern, I would presume that for the stable phases and the confirmed phases, you would have experimental data to train your system. Now, when it comes to these predicted phases, you would have to train them with simulated data. My analogy is like Cinderella that wants to have the pigeons tell apart the lentils of peas, and to train them with sort of plastic peas. Or so, how critical is it, or what would be your first of all, is it a concern to train with one part with actual data and part with simulated data? And what would be the thing to pay attention to for the simulated data?
Yeah.
So obviously you want to get as close to reality as possible, but what's the most important issue for training purposes?
Right. So the question is, what are the, because I'm the only one mic'd, so I'm trying to repeat the question to be able to,
train with simulated.
how can we properly train simulated data to be able to find these rare events?
And if I may add to this, what is simulated data?
Right.
Yeah,
We would love to understand that because.
Right. Sorry, I didn't touch on that too much. So let me start with the first question. What is simulated data? I would say simulated data is a realistic view of the structure and the microstructure that we have. So you go from, if you have a DFT simulation of, you have your unit cell, you can use that in order to create your diffraction pattern and at least the intensities of the structure factors that's always going to work. You can always calculate that. And if you have a more complex microstructure, like a molecular dynamics simulation, you can do the same thing. It's a little bit more computationally intensive, but you can still simulate the diffraction pattern, electron, or even the image that you might see. So that's the simulated data. That's what I would say. And so starting with the structure factors of an unknown phase, and also so you have the intensity of the Bragg spots, and you also have their position or their magnitude and their relative symmetry. So that's sort of the information that you can compare directly with the experiment. Now, searching for this needle in a haystack is easy when the structure that you're looking for is very different from all other known structures. So when the unit cell is different by multiple fractions of a percent, basically. So there you can really see that, oh, my Bragg spot is at a different Q vector, it's at a different radius on my detector, and so this is sort of a smoking gun. But if you still have some ambiguity, there could still be an ambiguity in the phase that you assign to that. So there could be other phases that also overlap with that. So you have to use more complex approaches. And this is something that I'm working on also in collaboration with Aijan and our student Rasul, to be able to separate this and solve this problem of the ambiguity that still exists. And yeah, how do you approach this problem? Well, I think you start with something that, like I said, is easier, and then we work our way to the harder problems. And how do simulations help that? Well, as you increase the complexity of the simulation, make your molecular dynamics simulation more and more realistic, it only becomes a tool. And then you can iterate on the data analysis itself. This is something I did during my PhD. I tried to bridge molecular dynamics with powder diffraction to train the analysis on the complex molecular diffraction or molecular dynamics simulations. And then once you have a good sort of knowledge of what the limitations of your analysis is, apply it. And then you also have better error bars in your recovered analysis, I would say. So you can train it on more and more sophisticated models for your structure and microstructure. And then I would apply it to experiments.
Yeah. Okay, just a comment on the answer. I think it's very dangerous between code to train a system with a simulated rate. Because in that case, you would assign, or you could assign one of these rare events to a phase which actually doesn't exist. Right? So, at least if you do that, you have to be aware that it is actually the biggest bias that you can include in the system.
Yeah.
And actually, this brings me to my other question. In all the examples that you gave, we see that it's already extremely complicated, and you have a lot of computational power to do that. You always assume that you know the solution. You always have a guess. This is already, asking for a lot of computational power or calculation. But what if I don't know at all? Let's rephrase it another way. How long or how more powerful should be the computer in order to have a database which has, let's say, all the solution, and then you can find something that you don't know? Because here you said, I have to look on HDL and how I can rotate it and how I can do a linear function. It means that you know the HDL. So basically, you know what you're expecting.
Yeah.
If it is one phase, it's okay. If you have 10 phases, it becomes extremely complex.
Sure.
But you still know.
Yeah.
You still have a guess of what are these 10 components. So now, if I don't know the components, how far are we from that?
So your question is, how far are we from real ab initio analysis without any assumption, without even relying on a database to compare to? And I would say that these work well when you have high quality. So the Fourier transform approach that I showed you, you don't have to assume anything. You can just from the image, you can already obtain information about the unit cell, the orientation, the space group, or certainly the point group. Space group, you need more information. So, so that aspect works well again for the single crystal case. Now, what happens when you have overlapping information on your detector? And that's sort of the problem that I tried to say, is that we have enough pixels in order to do this, but our algorithms need to be a little bit more sophisticated in order to be able to have the same ab initio approach. Of course, I want it to be ab initio as possible, introduce as little bias as possible. I mean, and even go to the level of using the coherent source, you can actually solve for the image itself using iterative phasing approaches where you, again, assume randomness for the initial phases. So it's an ab initio imaging approach. And merging all of this together, I mean, it's constantly getting cycled back around. So the phase problem started in crystallography, and then it was introduced into imaging again, and then it's coming back around into crystallography, and it'll come back around into imaging again. And so, but I just wanted to give a little bit of a state of the art, that it works well for small unit cells, few numbers of atoms in the unit cell, high quality single crystal data. Then you can do things very ab initio. But as you see, if we're really looking at these transient occurrences, the possibility of that happening is nearly zero. So if we really want to say something meaningful, we have to chip away also at the analysis algorithms that we're developing. So yeah, that's sort of my answer.
Questions?
Yeah.
In the slide 41, we're comparing simulated data with the experimental data.
Yeah.
Yeah.
This is actually all simulated.
This is
Sorry.
all simulated.
This is all
I
simulated.
just wanted to know what means in simulated data crystal per image. It's the unit cell or the input file that you use?
No, the number of overlapping diffraction patterns that I put in a detector. So this is the diffraction pattern from one crystal. And this is the diffraction patterns from like 10 crystals. So at different random orientations of the crystal. I just assume that I have them in the beam altogether. So that's what I mean by crystals per image. Okay.
Any other questions?
With your super microscope that you showed at the beginning, when you want to observe the phase transformation, how do you induce those phase transformations? I know that you can shine a laser on the sample. What else? Can you change the pressure? Something?
Well, yeah, if we can design a sample holder for it, then it can, if you can do it in a TEM environment and it's thin enough, then it's possible. I mean, people do, there's flow cells that you can, and if you have enough money, of course, that's the other limitation, the real world limitation. But in the real perspective of what's physically possible, yeah, you can electric field, electric current, pressure, temperature, chemical, gaseous environment, liquid, solvent mixings, solid state interactions.
How do you synchronize if it's not optical? Because you do pump
Yeah.
That's
Yeah.
why you are using light. Because
Yeah.
the laser light is actually generating.
Yeah, absolutely, absolutely. It's on a different time scale, of course, so too.
Yeah, but we have some. Let's say,
You're limited, there's other limitations based on the diffusion of,
the problem is synchronization. I discussed that with before we hired possible to do that magnetically or electrically, and the answer was no, because we cannot synchronize. We don't know
oh yeah, you can send an electric pulse, such as a nanosecond into your material.
We have phenomena like
Yeah.
which are 30 per second, right? So we need absolutely to synchronize
Yeah.
the beginning of the
Yeah,
transition.
yeah, yeah, You need to synchronize, yeah. Yeah, you can, as long as it's synchronized. So the master clock on the DTEM is the detector. So that sends a signal to the laser, actually. So we already are synchronizing the laser with the detector. And so there's also the auxiliary possibility of plugging in another sort of trigger. So then you would trigger your electric current with that same master clock, basically.
The resolution would be the same.
No.
Because you have your 10
Yeah,
resolution,
yeah.
but you have the transient
Yeah. Yeah.
It will be limited by the electronic response time, right?
It depends on what you're trying to do. I mean, your trigger will be for a slow thing like pressure, like you put a little AFM tip sort of, and you try and press on your material and you look at that deformed region. That is a slower process because that's a mechanical sort of movement. And so, but people have done this where you can look on the microsecond time scale or the millisecond time scale.
Yeah, with such time scale.
So the longer time scale, with the shorter time scale, well, I'd like to. I'm working with Jin Yang in order to push the time resolution faster than a nanosecond on the DTEM, developing the compressed sensing, which is a whole nother data analysis question mark.
Well, we are already past our seminar time, but before we go, I'm going to be selfish. I'm going to ask one quick question for the student and the people who might be watching online. So to work in your field, Ken, I guess the student has to have background in classical mechanics to do molecular dynamic simulations as well as the microscopy. Is that right? So
Yeah. You have to be a curious physicist.
perfect. That's a great answer. Okay.
And then anything is possible. Then you can sit down and program a computer, or you can sit down and tinker with a
Perfect.
microscope.
I like that answer. Thank you so much, everyone, for coming, and let's thank our speaker again.